Tonight, if you look far enough into the darkness of the sky, you're not just seeing stars, you're seeing moments that left the universe millions, even billions of years ago. But the stranger question is this: if light could travel far enough, bend long enough, and somehow return, could we one day see our own past? Could the night sky be not only space, but a gigantic mirror of time? Welcome to Drift into Quiet Knowing. In today's quiet journey, we will step into one of the most beautiful truths in astronomy. Everything you see arrives late. Light from the moon takes a little more than 1 second to reach your eyes. Light from the sun needs about 8 minutes and 20 seconds to cross the distance between the sun and Earth. And light from the Andromeda galaxy, the Milky Way's large neighbouring galaxy, began its journey about 2.5 million years ago before it finally reached us. That means when you look up at the sky, you're not truly seeing the universe as it exists right now. You're seeing memories made of light. A star may have changed, a galaxy may have grown older, a distant cloud of gas may have given birth to new suns, but the image that reaches your eyes is an image of the past, sent out before our present had time to take shape. And if you stay until the end of this video, you will understand why a telescope is not only a tool for seeing far away, but a machine for looking back in time. You will understand why we can see galaxies when they were still very young, why there is a natural limit beyond which light cannot tell us everything, and why the question, if we look far enough, are we seeing ourselves, leads to an even deeper mystery: the true shape of the universe. Now, let your body slow down a little. Let your mind grow calm, like starlight falling onto the surface of a dark lake, and come with me into the deep sky, where every ray of light is a fragment of the past, and every patch of darkness may be holding a very ancient answer. Let us begin with something very close. So close that in everyday life we usually do not notice it. When you look at your hand, you feel as if you're seeing it instantly. When you look at a cup on the table, a lamp in the room, or the face of someone sitting in front of you, the world seems to appear in your eyes all at once. But physically, that is not entirely true. Your eyes do not touch objects directly. Your eyes receive light. And light, even though it is so fast it is almost impossible to imagine, still needs time to travel from one place to another. Inside a small room, that amount of time is far too tiny for our brains to notice. Light moves so quickly that the entire world in front of us seems to be present at the same time. But that sense of at the same time is only a human feeling, not the way the universe truly works. If light needs time to travel, then every act of seeing is a late arrival. Every image entering our eyes is news from a moment that has just passed. For things very close to us, that past is far smaller than the blink of an eye. But as distance grows, that delay is no longer a tiny detail, it becomes a timeline. Look at the moon. The light reflected from its quiet grey surface takes a little more than 1 second to reach your eyes. That means the moon you see is not the moon of this exact present moment, but the moon from a little more than 1 second ago. That may not sound like much. 1 second is only a short breath, a small silence. But it is enough to remind us that no view in the universe is completely instant. Then look at the sun. Light from the sun needs about 8 minutes and 20 seconds to cross the space between it and Earth. If the sun could suddenly change right now, we would not know it immediately. The sky would continue telling us the old story for more than 8 minutes. This is the first point we need to hold clearly in our minds. Looking far away is not only looking across space, but looking through time. Distance in astronomy does not only tell us how far away something is, it also tells us how old that thing's image is by the time it reaches us. A light year is not a unit of time, but the distance light travels in 1 year. But because light spends 1 year crossing that distance, when we look at a star 1 light year away, we are seeing light that began its journey 1 year ago. If a star is 100 light years away, the image we see is the star as it was 100 years ago. If a galaxy is millions of light years away, its light left that place when Earth was living through a completely different chapter of its history. The night sky, then, is not a live photograph of the universe as it is right now. It is more like a silent library, where the pages arrive from many different ages. One star may give us light from a few decades ago. One star cluster may give us light from thousands of years ago. A distant galaxy may appear as it once existed before human beings appeared, when ancient oceans were still changing, when the continents had not yet taken the shapes we know today. The deeper the space, the older the time, and the farther we look, the more we leave behind our familiar present. This is what makes astronomy such a special science. Geologists read the past in rocks. Biologists read the past in fossils and in genetic code. Historians read the past in texts, buildings, and traces of civilization. Astronomers read the past in light. A telescope is not just a large tube that magnifies the sky. It is an instrument that gathers signals that have travelled through space for so long that time itself becomes part of the data. When a telescope points toward a distant galaxy, it does not see that galaxy as it is now in some absolute sense. It sees that galaxy at the moment its light left it. If the light has travelled for 1 billion years, the image that reaches us is a 1 billion-year-old image. The wonderful thing is that this light carries more than appearance. It carries information. In the colour of the light, we can read temperature. In spectral lines, we can recognise chemical elements. In the way light shifts toward the red, we know the light source is moving away from us in an expanding universe. In the faint brightness, the blurry shape, and the structure of the galaxy, we can see how matter once gathered together in the distant past. That is why, when large telescopes like Hubble or James Webb observe very deep regions of the sky, they are not simply photographing distant objects. They are helping us look back at old chapters of the universe. We can see galaxies when they were much younger than the galaxies around us today. We see places where stars are forming violently. We see unstable structures, clouds of gas and dust, stars and gravity pulling together into giant cities of stars. Because light arrives late, the universe allows us to observe many different eras at the same time on the same sky. There is something here that can easily cause confusion. When we say a galaxy is billions of light years away, we may imagine light travelling through fixed space like an arrow flying across a gigantic room. But the universe is not a room standing still. Space itself is expanding. During the time light travels to us, the distance between regions of space also changes. So the numbers in cosmology need to be understood carefully. Some light has travelled to us for more than 13 billion years, but the region of space that emitted that light may now be much farther away than 13 billion light years, because the universe has expanded throughout the light's journey. This is not a contradiction. It is a sign that time, light, and space in cosmology cannot be separated the way our everyday intuition wants to separate them. If we go even deeper, we come close to one of the natural walls of observation. The universe is about 13.8 billion years old, but we cannot look with ordinary light all the way back to the very first moment in a simple way. In the very early universe, everything was so hot and dense that light kept colliding with charged particles. It could not travel freely over long distances. The universe was like a glowing fog of fire, where light was trapped in a sea of hot matter. Only when the universe expanded and cooled enough could electrons combine with nuclei to form neutral atoms. Then light was no longer constantly scattered. The universe became transparent. The ancient light left over from that moment is now called the cosmic microwave background radiation. It is not light from one specific star, and it is not an image of a galaxy. It is the thermal afterglow from when the universe was still very young, about 380,000 years after the hot, dense beginning we call the Big Bang. When astronomers observe the cosmic microwave background radiation, they are not seeing the Big Bang directly. They are seeing the oldest light that can freely reach us through electromagnetic radiation. It is like the universe's first baby picture, not the moment of birth, but an extremely early trace of the universe's childhood. And this is where our question becomes deeper. If looking far away means looking into the past, and if old light is still reaching us from distant ages, then where is the light that left Earth in the past? The rays of light reflected from ancient oceans, from primeval forests, from the first cities, from the faces of people who lived and disappeared, all of them once left Earth. They flew out into space at the speed of the light. In principle, a tiny fraction of them is still spreading through the universe as a fragile wave of history. If there were an observer 100 light years away from Earth, and if that observer had a telescope so perfect it would be almost unreal, they would not see Earth as it is today. They would see Earth as it was 100 years ago. If there were an observer 1,000 light-years away, they would see light that left Earth 1,000 years ago. If they were millions of light-years away, they would see this planet before modern humans built civilization. Of course, this is an example of the principle of light, not an easy real-world technology. The light reflected from Earth is too weak, too scattered, and would be drowned out by the powerful light of the sun. But physically, that message of light has already left. Now let us turn the question back toward ourselves. Could we see our own past? For that to happen, the light that once left Earth would have to do more than fly away. It would have to return. A ray of light from Earth's past would have to travel through the universe and then, by some path, come back to our telescopes. If that happened, we would not be seeing an ordinary mirror. We would be seeing Earth as it was when that light left. But in a large flat space with no mechanism to bring light back, light does not automatically circle around. It keeps travelling farther away, growing weaker, spreading wider, and almost disappearing into the ocean of signals in the universe. So the possibility of seeing ourselves in the past does not depend only on how powerful our telescopes are. It depends on the deep shape of space. If the universe is infinite and nearly flat on large scales, light leaving Earth will keep going, with no natural reason to return to the place where it started. But if the universe is finite in a special way, or if it has a closed spatial structure, light could theoretically travel along a very long path and come back from another direction. This is not a mystical idea. It belongs to the field of cosmic geometry and the global structure of space. To imagine it more gently, think about the surface of Earth. If you travel straight long enough across the surface of the planet, ignoring mountains, oceans, and every obstacle, you could return close to your starting point. Earth's surface has no edge, but it is finite. Still, this example only helps our intuition become familiar with the idea of being finite but without an edge. The three-dimensional universe does not necessarily work like the two-dimensional surface of Earth. The geometry of space may be flat, positively curved, negatively curved, or more complicated through what is called topology. Topology does not only ask how much space curves, it also asks how space is connected to itself. If the universe had a closed structure small enough in some direction, a galaxy could appear many times in the sky, with each image arriving through a different path of light and from a different moment in the past. In that case, we could see the same region of the universe in several different ages. Cosmologists have looked for signs like this, especially in the cosmic microwave background radiation. If the ancient sky had repeating patterns that followed a special rule, that could suggest that light had looped around through the global structure of space. But so far, there is no solid evidence that the universe has a closed size small enough for us to see copies of the very region of space we live in. This is a point we need to say very carefully. Science does not say that seeing our own past is certain. Science also does not say that it clearly can happen in the universe we have measured. The honest answer is this: looking far away is definitely looking into the past, but seeing our own past is only a theoretical possibility in certain very special models of the universe, and right now there is not strong enough observational evidence to say that it is happening. The beauty lies in that caution itself. An idea can make the imagination tremble, but it still has to pass through the door of measurement, data, and verification. There is another way light can be bent: gravity. According to general relativity, mass and energy curve space-time, and light follows curved paths through that geometry. This is why we can observe gravitational lensing. A large galaxy cluster can bend the light from a more distant galaxy behind it, creating arcs of light, stretched images, or even multiple images of the same celestial object. In special cases, light travelling along different paths can reach us at different times, like several versions of a faraway event. But gravitational lensing does not mean that light from Earth can easily return so we can see ourselves. It only shows that space-time can bend the path of light, and that the universe sometimes behaves like a gigantic optical system. If a supermassive black hole or a gigantic gravitational structure were in exactly the right place, light could be strongly redirected. In theory, there are very special light paths around black holes, where photons can circle near a region called the photon sphere. But those paths are unstable, and this does not create a simple cosmic mirror for humans to look back at their own past. The universe does not easily return light like a reflective wall. Light is a faithful messenger, but it does not turn around on its own. It follows the geometry space-time allows. So if we ask with precision, when we look far enough, are we looking into our own past? Then the answer has to be divided into two layers. The first layer, we are definitely looking into the past. Every star, every galaxy, every deep region in an astronomical image is late arriving light. The second layer is that our own past. Based on what science knows today, almost certainly not in a direct sense. We are not seeing ancient Earth reflected from a closed loop of the universe. We are not seeing our own faces at a moment that has already passed, but we are seeing something perhaps even deeper, the past of matter, the past of light, the past of the conditions that made our existence possible. The atoms in your body did not appear in isolation. The hydrogen in water and in biological molecules has its origin very early in the history of the universe. The carbon in your cells, the oxygen in your blood, the calcium in your bones, the iron in your hemoglobin, and many heavy elements were created in generations of stars and in violent cosmic events. When a large star lives and dies, it scatters heavy elements into space. From that material, new stars, new planets, and eventually living bodies can form. Looking up at the distant universe is not only looking outward. On a very deep level, it is looking back at the material family tree of ourselves. A distant galaxy is not a quiet decoration in the background of the sky. It is evidence that the universe was once different. The cosmic microwave background radiation is not just faint noise in a detector. It is the trace of a time when the universe had just become transparent enough for light to begin its long journey. An old red star is not just a beautiful point of light. It is a chapter in the life of matter. And Earth, the place where we stand, is also sending out its own light. Night after night, day after day, generation after generation, this planet sends faint signals into space. Most of them will never return to us, but that thought does not make the universe colder. It makes every moment more extraordinary. Because even our present is becoming the past for some place far away. Imagine a distant planet 65 million light-years from us. An observer there, if they had an impossible device sensitive enough to distinguish tiny Earth beside the light of the sun, might be receiving light that left our planet during the time when the last dinosaurs still existed. To them, Earth would not be a world of cities, satellites, and oceans measured by modern machines. Earth would be an ancient planet, where the continents and living creatures carried a different story. And for someone only a few dozen light-years away, the faint radio signals of technical civilization may only just be beginning to arrive. The universe then does not have one single present that is easy for intuition to grasp. Each location receives a different version of history, depending on how long the light took to get there. This does not destroy reality, it only makes reality more subtle. In everyday life, we live by a very practical idea of now, but in the vast universe, now is no longer a single curtain spread evenly over every place. Relativity has taught us that time and space are connected to the observer, to motion, to gravity, and to the way signals travel. No information can travel faster than the speed of light in a vacuum, so if we want to know what a distant place is like, we have to wait for light, or some other form of physical signal to arrive. Astronomy is the art of being patient with the universe's delay, and that very delay creates the beauty. If light travelled instantly, the sky would give us a flat, simultaneous present. But because light has a finite speed, the sky becomes a depth of time. Every distance is a layer of age. Every image is an old story. A telescope is like a giant ear listening for distant echoes, except instead of sound, it listens with light. It does not pull the past back. It simply receives what the past is still sending. When we ask whether we can see ourselves in the past, perhaps we're asking something deeply human. We want to know whether time leaves behind a path of return. We want to know whether what has been lost is truly gone, or whether it's only very far away, travelling along the path of light. Physics answers with precision. Light leaves, information spreads. But to observe ourselves again, we would need very special geometric conditions for which we have not found evidence. But astronomy also gives us a gentler answer. The past does not completely vanish from the universe. It is encoded in light, in spectra, in the composition of stars, in the ancient microwave background, and in the elements that travelled from the hearts of stars into living bodies. You do not need to see your own face from many years ago in the sky to understand that you are part of the universe's past. Every breath has a material history. Every heartbeat runs on atoms created through many generations of stars. Every time you look up at a distant point of light, you are meeting a signal that has crossed space for far longer than a human lifetime. And when that signal touches your retina or the sensor of a telescope, that past becomes part of the present for one brief moment. That is why today's question is not just an intellectual game. It is a doorway into the way the universe stores time. If we look far enough, we are looking into the past, but perhaps not our personal past as if in a mirror. We are looking into a larger, deeper, older past. The past of light, of stars, of galaxies, of the very ingredients that created Earth and life. The sky does not give us back an old photograph of ourselves. It gives us a long map of origins, and once we understand that, the night sky becomes different. It is no longer just a black curtain with bright dots. It is a space where many ages appear together. The moon comes from a little more than 1 second ago. The sun comes from more than 8 minutes ago. Andromeda comes from about 2.5 million years ago. Deeper galaxies come from when the universe was young. The cosmic microwave background radiation comes from the time when the universe had just become transparent enough for light to travel freely. All of those layers overlap in a single view. And in that view, we recognize a very quiet truth. Our present is also becoming old light for someplace out there. From that truth, we can understand why a telescope is not just a tool for seeing far away. More precisely, a telescope is an instrument for receiving the past. It does not bring galaxies closer to us the way a magnifying glass brings tiny letters closer to the eye. It does not shorten the distance between Earth and the stars. What it does is far more subtle. It gathers particles of light that are too faint, too distant, too old. Particles of light that left the place where they were born long before they touched a human mirror, lens, or sensor. The larger a telescope is, the more it resembles a wider lake placed beneath a very sparse rain. If the rain of light falls only a few drops at a time, a small cup will receive almost nothing. But a wide lake can gather enough of those rare drops for us to know that, somewhere out there, it truly is raining. The universe works the same way. Many galaxies are so far away that by the time their light reaches Earth, it is only a faint stream of signals. The human eye cannot recognize it, but a large telescope can patiently collect each photon, each tiny particle of light, until the ancient picture begins to appear. The miracle is this: those photons are not new. They were not just created near Earth. They have traveled through space for many years, many millions of years, even many billions of years. When a photon leaves a distant star, it carries information about that star at the exact moment it was emitted. It does not update the news along the way. It does not know how the star changed after that. It only faithfully carries a fragment of the past, crossing the darkness, passing through expanding regions of space, moving through thin dust and gravitational fields, and finally touching our observing instruments. An astronomical image, then, is not a photograph of the absolute present. It is a late meeting between the observer's present and the light source's past. When we look at a deep image of the universe, we often see thousands of tiny points and streaks of light. Some points are stars in the Milky Way, relatively close to us. Some streaks are galaxies millions or billions of light years away. They are in the same image, but they are not in the same historical moment. One point of light may be a few thousand years old. Another faint streak may be light that began its journey before Earth had complex life forms like the ones we know today. A tiny red dot may be a signal from the time when the universe was still young. In a single frame, a telescope places many overlapping layers of time before our eyes. That is why saying a telescope sees far away is not enough. It sees old. An archaeologist digs into the ground to find layers of humanity's past. Each layer of soil, each shard of pottery, each trace of ash, each stone tool tells a story of a time that has disappeared. An astronomer does not dig into the ground. An astronomer looks up at the sky. But at a deeper level, there is a beautiful similarity. They are also reading layers of the past, except those layers are not beneath their feet. They are in the light arriving from far away. A telescope is astronomy's very delicate shovel, and light is the sediment of time. When a telescope points toward the moon, it receives light that is just a little more than 1 second old. When it points toward Jupiter, the light may have travelled for tens of minutes, depending on where the two planets are in their orbits. When it points toward a nearby star, the light may have travelled for many years. When it points toward Andromeda, the large galaxy near the Milky Way, the light has travelled for about 2.5 million years. This means the picture of Andromeda we see does not tell us exactly what Andromeda looks like at this moment. It tells us what Andromeda looked like when that light left it, at a time when the ancient ancestors of human beings had not yet entered most of the story of civilization. And when we go even farther, telescopes begin to do something ordinary imagination can barely keep up with. They show us galaxies not in a mature stage, like many galaxies near us, but at younger stages of life. Some distant galaxies appear small, faint, red, and sometimes distorted, because their light has been stretched by the expansion of the universe. That reddening is not simply a beautiful colour in an image. It is a physical trace of space stretching while light travels. When the wavelength of light is stretched, the light shifts toward redder wavelengths, and for very distant galaxies, light that once belonged to the visible range may have shifted into the infrared range. That is why infrared telescopes such as the James Webb Space Telescope have a special ability to look into the very distant and very ancient universe. Imagine a letter written in blue ink, but during a very long journey, the paper is stretched so much that the letters stretch too, and the spaces between the strokes grow wider. When the letter reaches us, it still carries old information, but its shape has been changed by the journey. Light from a distant galaxy is like that. It still carries traces of where it was born, but the expanding universe has stretched its wavelength. Astronomers do not simply look at an image and guess. They measure the spectrum of light, analyze absorption and emission lines, compare them with known physical patterns from the laboratory, and from there infer the chemical composition, temperature, motion, and redshift of the light source. Spectroscopy is one of the quietest miracles in science. When light from a star or galaxy is separated into many wavelengths, it becomes something like a fingerprint. Hydrogen, helium, oxygen, carbon, iron, and many other elements leave their own marks in the spectrum. If those lines are in familiar positions, we know the source is relatively nearby or has not shifted very much. If they have been pulled toward the red, we know the light has travelled through an expanding universe and that the source belongs to a more distant past. In this way, a telescope does not only create beautiful images, it turns light into evidence. That is what makes astronomy different from pure daydreaming. When we say a distant galaxy is being seen as it existed billions of years ago, that is not a poem. It is a conclusion based on the speed of light, spectroscopic measurements, models of cosmic expansion, and many layers of verification. The beauty of the universe does not need to be exaggerated into falsehood. The truth itself is already strange enough. As long as light has a finite speed, and as long as space is large enough, the sky naturally becomes a museum of time. There is one point we need to understand clearly. A telescope does not travel into the past in the sense that our physical objects leave the present. The telescope is still here, in our present. But it receives signals that were emitted in the past. So it is like a person standing on the shore today, finding a glass bottle that contains a letter released into the ocean many years ago. That person has not truly returned to the moment when the letter was written, but the contents of the letter allow them to know something about that moment. A telescope is the same. It stands in the present, but the light that reaches it is a very old letter. Every time a telescope opens its eye to the sky, it is not asking the universe a simple question like, "What is out there?" It is also asking, "What was out there like?" This is why deep images of the universe are worth more than beautiful scenery. They are records of cosmic evolution. If nearby galaxies show us mature structures with spiral disks, regions of old stars, regions of young stars, and vast halos of dark matter, then more distant galaxies show us periods when structures were forming, colliding, merging, and powerfully creating stars. Looking from near to far, we are not only moving through space, we are moving through stages in the development of the universe. But to see those ancient signals, telescopes must overcome many limits. The first is faintness. Light spreads out as it travels. The farther away a light source is, the less energy reaches each unit of area. A galaxy may contain billions of stars, but when it is billions of light years away from us, it becomes only an extremely faint speck. That is why telescopes need large mirrors to collect more light. They also need long exposure times to build up the signal. Some deep images are not created from a quick glance, but from many observations, many hours, many days, and sometimes very carefully combined data. The second limit is Earth's atmosphere. The atmosphere protects life, but for astronomy, it also blurs and distorts light from the universe. Moving air makes stars twinkle. Water vapor and molecules in the atmosphere absorb some wavelengths. This is why space telescopes are especially valuable. When Hubble was placed above most of the atmosphere, it could observe the sky with a sharpness far beyond many ground-based observations from the same era. It was not the largest machine ever built, but its position in space allowed it to view the universe with a very steady eye. Then came the James Webb Space Telescope, designed to observe strongly in the infrared range. This is very important to our story, because light from extremely distant galaxies has been shifted into the infrared by the expansion of the universe. If we want to find very early galaxies, we must look at the wavelengths that ancient light has become after its long journey. To put it gently, Webb does not only look into the darkness, it listens to colours that have been stretched by time. It searches for signals the human eye cannot see, but physics can read. When scientists release deep observations from Webb, what overwhelms many people is not only the beauty of the images, but the age of the light. A tiny speck in the dark background may represent a galaxy from when the universe was only a few 100 million years old. Pause for a moment with that idea. The universe today is about 13.8 billion years old. If we see a galaxy as it existed when the universe was only a few 100 million years old, that means its light has travelled across almost the entire history of the universe to reach us. That fragile signal has crossed time far longer than the age of Earth, longer than every civilization, longer than every human story ever told, and in the moment it touches the telescope mirror, that past becomes data. Not myth, not rumour, data, numbers, wavelengths, brightness, redshift, shapes, measurement uncertainties and models to be tested. That is the special beauty of science. It lets us touch what cannot be touched by hand, while still keeping humility before what remains unknown. An astronomer can look at a faint red speck and avoid saying too much too quickly. They ask, what does this light spectrum look like? Could this truly be a very distant galaxy? Could a nearer object be causing confusion? Do we need additional observations? That carefulness is what makes the story of looking back in time trustworthy. Telescopes also teach us that an image is not always the final answer. In many cases, the image is only the first doorway. Behind the image are spectroscopy, distance measurements, models of stars, models of dust, models of gas, and comparisons with cosmological simulations. A distant galaxy may appear very red because it is truly very far away, but it may also look red because it contains a great deal of dust that absorbs more blue light. To tell the difference, astronomers need multi-wavelength data and careful analysis. This is very important if we want to keep our story scientifically accurate. The deep universe is not a place for rushed conclusions. It is a place where every weak ray of light must be asked very slowly. Where did you come from? How long have you travelled? And what traces do you carry? On that journey, there is one phenomenon that makes a telescope seem as if the universe has lent it an extra natural lens. That phenomenon is gravitational lensing. When light from a very distant galaxy passes near a massive galaxy cluster along the way, the gravity of that cluster can bend the path of the light. As a result, the image of the background galaxy can be magnified, stretched into arcs of light, or appear as multiple images. This is not because there is a gigantic glass lens in outer space, but because space-time itself is curved by mass. With strong gravitational lenses, astronomers can observe objects that are farther and fainter than they normally could, as if the universe itself were handing us a tool of assistance. But gravitational lensing also reminds us that light does not travel through an empty stage. It travels through a structured universe. It can be bent by galaxy clusters, absorbed by dust, stretched by expansion, and weakened by distance. Every photon that reaches us is a tiny survivor of a long journey. It does not only speak about where it was born, it also carries traces of the path it has travelled. So when a telescope gathers light, it is reading both origin and journey. It reads the place that emitted the light, and it reads the universe in between. At this point, the question, can we see our own past, begins to have a clearer foundation. If a telescope is a machine for receiving the past, then in principle, The light that left Earth in the past is also a kind of data. Rays of light reflected from oceans, clouds, mountains, forests, cities, and human faces have left this planet. They also obey the same speed of light. They also fly into space. An observer far enough away, if they had technology far beyond our current abilities and could separate Earth's signal from the light of the sun, would receive an image of Earth's past. Not because time has reversed, but because light arrives late. But the telescope itself also helps us understand why that is almost impossible for us in a direct sense. We can collect light from elsewhere because that light is travelling toward us. But the light that once left Earth is travelling away from us. To see it again, we would need that light to return, or to be bent along a special path, or for the universe to have a global structure that makes the path of light loop back. No matter how powerful a telescope is, it cannot create the past by itself if the signal does not arrive. It does not call light back. It only receives what the universe sends. This is a deep lesson about the limits of observation. Science is not only about knowing more, science is also about knowing what can be known, how it can be known, and where the limits are. A telescope is a time machine in the sense that it receives old light, but it is not a machine that controls time. It does not let us choose a day in the past and open it like a movie. It only gives us the signals that are arriving from the directions light has truly travelled. So the sky is not a complete archive of every moment. It is an archive of the signals that can still reach an observer. That makes every observation more precious. When a telescope gathers light from a distant galaxy, it receives a unique chance to learn about an era that cannot be recreated in a laboratory. We cannot build a young universe in a laboratory. We cannot rewind the entire history of a galaxy. But light has travelled from that era to this place. It is natural evidence. It is an experiment the universe has already performed, and we are the late arrivals who have learned how to read the result. Perhaps that is why deep space images often create such a strange feeling. We know we are looking at tiny points of light, but inside it can feel as if we are standing before an abyss of time. A speck of light is no longer just a speck of light. It is a distant city of stars seen when it was much younger. A curved streak is no longer just a curved streak. It may be light whose path has been bent by space-time. A dark background is no longer just emptiness. It may be a place containing signals that are too weak, too far away, or not yet able to reach us. The more we understand how telescopes work, the more we realize the sky is not silent. It is speaking, but in a very slow language. And that language is not only made of images. Sometimes the most important thing is not what looks most beautiful to the eye, but a tiny line in a spectrum, a very slight difference in brightness, a sign that hydrogen gas is emitting light, an absorption line showing the presence of heavy elements, or a redshift showing that light has been stretched across billions of years. To the ordinary eye, the universe is a starry sky. With telescopes and spectrographs, the universe is a physical text. Each wavelength is a letter. Each spectral line is a punctuation mark. Each source of light is a paragraph written in heat, gravity, atoms, and time. If we hold on to one core idea throughout this journey, it becomes very clear. Looking far away means looking into the past, but not necessarily into our own past. Telescopes prove the first half of that sentence every night. They show us the sun from 8 minutes ago, stars from many years ago, galaxies from millions of years ago, and the distant universe from billions of years ago. But they also teach us the second half. To see our own past, our own light would have to return. If no signal comes back, there is no image to collect. Astronomy's time machine does not work through desire. It works through light that truly arrives. I want you to imagine a large telescope opening in the darkness, quiet and unhurried. It does not chase the stars, it simply stands still and waits for light to come. Some photons left their sources when there were no modern humans on Earth. Some photons left their sources before the Sun and Earth formed, if we are speaking about more ancient signals from the background of the universe. Some photons come from a region where the first stars were beginning to enrich the universe with heavy elements. All those particles of light travel through a long journey, without knowing that at the end of the road there are tiny living beings trying to understand their own origins. And perhaps this is the most moving part. A telescope is a time machine, but it does not separate us from the present. On the contrary, it makes the present wider. When an ancient signal touches a telescope today, the distant past enters the present of understanding. A young galaxy is no longer only something that once existed, it becomes something being understood, being measured, being placed into the larger story of the universe. Our present expands to hold ages that the human body could never live through. So when you look at an image from a deep telescope, do not only ask how beautiful the image is, ask how long the light inside it has travelled, ask what stage the universe was in when that light left its source, ask what traces it carries of which atoms, which stars, which motions. When you ask that way, an astronomical image is no longer a still wallpaper. It becomes a conversation between the present and the past. And that conversation leads us to the deeper part of the original question. If a telescope can see galaxies as they once existed, if it can collect light that has travelled through most of the universe's lifetime, if it can turn faint photons into history, then where is Earth's old light now? Does it still carry images of lost ages? Could someone out there see it? And in a universe with a special shape, could there be a path that allows those fragments of light memory to return to us? That question is no longer a simple fantasy. It has become a question about the shape of space, the limits of observation, and whether the universe allows light to loop back through itself. But before we arrive at that answer, we need to hold on to one fundamental truth. Every great telescope humanity has ever built remains humble before light. Telescopes do not invent the past. They do not decorate the past. They only receive the past when it arrives, and then use mathematics, physics, and patience to understand it. That is why a telescope is a real time machine in the most beautiful and honest sense, not a machine that carries our bodies out of the present, but a machine that allows the distant past to enter the intelligence of the present. When telescopes began looking deep into the universe, what they found was not just more galaxies, they found younger versions of the universe itself. This is what makes astronomy different from almost every other field of observation. If a biologist looks at a tree, they see the tree living right in front of them. If a geologist looks at a rock, they read traces of the past in its structure. But when an astronomer looks at an extremely distant galaxy, they are not just inferring the past from clues. They are directly receiving light that left that galaxy when the universe was much younger. That light is not telling a story that was written today. It is a story that began its journey billions of years ago and only now has finally reached us. The universe today is about 13.8 billion years old. That number is not just a dry timestamp, it is the baseline for the entire question today. If light takes time to travel, and if the universe has a finite age, then the deepest sky we can see cannot simply be an endless space in the ordinary sense. It is a history book opened by distance. Near us are objects whose light is younger. Farther away is older light. And the deeper we look, the more we move toward eras when stars, galaxies, gas, dust, dark matter, and space itself were still forming the great picture we see today. Imagine standing inside a very long museum. In the first room are photographs taken yesterday. As you walk farther, you see photographs from many years ago. Farther still, you come across images from centuries past. But in the Cosmic Museum, you do not walk with your feet. You walk through light. Every more distant galaxy is an older room. Every weaker signal is a deeper layer of time. And what is astonishing is that we are not only seeing the past of a few individual stars, we can see entire ages of the universe when the first galaxies were growing inside the primordial darkness. Very distant galaxies often do not look like the galaxies close to us. Many nearby galaxies have more familiar shapes, spirals, ellipticals, or structures that have settled over a very long time. But far away, when their light left them during the young universe, galaxies could be smaller, messier, colliding more often, and forming stars more intensely. They are like cities of light still under construction. Not every gravitational road has settled yet. Not every region of stars has aged. Gas is still abundant, gravity is still pulling matter into larger clusters, and the first generations of stars are beginning to change the chemical makeup of the universe. This matters a great deal, because the universe was not born with fully formed galaxies like the ones we see today. After the very earliest stage, matter was not distributed perfectly evenly. Some regions were slightly denser, and some regions were slightly thinner. Those tiny differences, under the influence of gravity, gradually grew larger. Matter pulled in more matter. gas fell into dense regions, stars formed, star clusters gathered together, small galaxies merged into larger galaxies. If we only look at the nearby universe, we see the mature result of that process. But when we look very far away, we have a chance to see that process while it is still happening. That is why deep telescope images are not just beautiful, they are evidence of cosmic growth. A faint red dot in an image may be a galaxy from when the universe was only a few 100 million years old. It is so small that it could easily be overlooked if we only looked with emotion. But to an astronomer, that tiny point of light may be an ancient record. It can tell us how early stars formed, how quickly galaxies grew, and how fast matter gathered into structure. Every discovery like this helps us test our models of how the universe went from a hot, dense, nearly uniform state to a place filled with stars and galaxies. But the closer we get to the early universe, the harder the light becomes to read, not only because the objects are distant and faint, but because the expansion of the universe has stretched the wavelength of that light. Light that once belonged to the visible range may be stretched into the infrared range after travelling for billions of years. So, to see very young galaxies, we need eyes unlike human eyes. We need infrared telescopes, cooled instruments, sensitive detectors, and long observation times. The early universe does not open its door with bright, easy-to-see light. It whispers through signals that are red, weak, and very far away. And then, when we keep asking, can we look even farther? The universe gives an answer that is both beautiful and limited. There is a light older than every galaxy we usually observe. It does not come from a star. It does not come from a planet. It does not come from a single galaxy. It comes from the moment when the universe itself became transparent. This is the cosmic microwave background, the leftover glow from when the universe was only about 380,000 years old. 380,000 years may sound enormous in human life, but compared with the age of the universe, it is like very early childhood. If the history of the universe were compressed into a human lifetime, that moment would be almost like the instant when the universe first opened its eyes. Before then, the universe was so hot and dense that free electrons were constantly colliding with photons. Light could not travel far in long straight paths the way it does today. It was scattered again and again like lamplight trapped in thick fog. Not because light did not yet exist, but because it could not yet freely carry information across vast stretches of space. As the universe expanded, it gradually cooled. At a certain point, electrons were able to combine with nuclei to form neutral atoms, mostly hydrogen and helium. When the number of free electrons dropped sharply, light was no longer scattered constantly. The universe changed from opaque to transparent. The photons released at that moment continued flying through space for more than 13 billion years, stretched by the expansion of the universe, until today they appear as cold microwaves filling the entire sky. This is one of the most beautiful achievements of modern science. We can measure that ancient light. It is almost uniform in every direction, but not perfectly so. In maps of the cosmic microwave background, there are extremely tiny temperature fluctuations. Those very small differences are not meaningless noise. They are traces of the seeds of structure. From slightly denser and slightly thinner regions in the early universe, gravity later built the cosmic web of galaxies, galaxy clusters, and cosmic voids. In other words, inside that oldest light is the first rough sketch of the galaxy-filled sky we see today. But the cosmic microwave background also sets a very deep limit. It is the oldest light we can directly observe using electromagnetic radiation. Before the universe became transparent, light could not travel freely to bring us a clear image. So when we say that looking far away means looking into the past, that is true. But it does not mean we can simply keep looking farther forever and see everything, including the very first moment. The universe has an early fog. The farther we look, the closer we get to dawn, but that dawn has a horizon. This horizon is not a physical wall somewhere out in space. It is not like an edge where the universe ends. It is the limit of the light-based information that can reach us. Beyond it, if scientists want to study what happened, they must use other methods. Inferences from particle physics, cosmological models, possible future gravitational waves, indirect traces in the cosmic microwave background, and the distribution of galaxies and matter. But with ordinary light, we cannot simply see through the era when the universe was still opaque. This reminds us that the telescope is a very powerful time machine, But it is not all-powerful. That limit also makes the original question sharper. If even the oldest light in the universe has an observational boundary, then seeing our own past does not depend only on distance. It depends on whether that light exists along a path that leads to us. We can see young galaxies because their light left them and travelled toward us. We can see the cosmic microwave background because those ancient photons were released when the universe became transparent and eventually reached human instruments. But the light reflected from Earth in the past is travelling outward in every direction. Without a path that brings it back, it does not become an image in our telescopes. Picture Earth on a night in the very distant past. The oceans reflect sunlight. White clouds drift by. Ancient forests absorb and reflect part of the light. Mountains, ice, sand, rivers, living things, everything sends tiny signals out into space. Those photons leave Earth. Some are absorbed by the atmosphere, some escape past the orbit of the moon, cross the paths of the planets, and keep moving beyond the solar system. After 1 year, they are 1 light year away. After 1,000 years, they are 1,000 light years away. After millions of years, they become a fragile sphere of light spreading through the Milky Way and beyond. Do those photons carry Earth's past? In principle, yes, but they are scattered in an extreme way. A small planet like Earth reflects very little light compared with the Sun. Its signal is weak, spread out, and mixed into a background that is much brighter. A distant observer who wanted to see ancient Earth would need technology far beyond anything we have today. Powerful enough to separate the planet's reflected light from the light of its parent star, sensitive enough to collect an extremely weak signal, and sharp enough to distinguish a tiny blue point across an enormous distance. But the important point here is not whether the technology already exists. The important point is the principle. Earth's past has already left by way of light. So if a civilization 65 million light years away had an unimaginable telescope pointed toward Earth, they would not see modern cities. They would receive light that left this planet near the end of the age of dinosaurs. If an observer 1,000 light years away could see clearly enough, they would see Earth from 1,000 years ago. If they were 100 light years away, they would receive the light of a century ago. This is not time travel in the sense of moving backward through history. It is the ordinary result of the finite speed of light. What happened here becomes the observed present somewhere else after a matching delay. But for us to see our own past, that light has to return. This is the key point we need to hold firmly. Looking far away means looking into the past, but not every past is sitting in front of us. A telescope only sees the past of sources whose light is arriving. Earth's past is spreading outward into the universe. It does not naturally arrange itself into a screen in front of us. Unless space causes light to loop back, unless a special gravitational structure sends the light back, unless there is a physical path connecting that signal to the observer again, we cannot simply look far enough and see ourselves long ago. This is why the question, if we look far enough can we see our own past, actually leads to a much larger question. What is the shape of the universe? If space on the largest scale is infinite, or simply so vast that our light cannot loop back within the lifetime of the universe, then the practical answer is no. If the universe has a special closed structure, then in theory light could travel along an extremely long path and return from another direction. In that case, one region of space might appear multiple times in the sky, each time at a different age. But so far, observations have not shown solid evidence that the universe is small enough or closed enough for us to be seeing past copies of ourselves. So we need to keep both boldness and humility. Boldness, because physics allows us to ask questions that sound like they belong in dreams. Can light circle through the universe? Can space be closed? Can the sky contain repeated images of the same region of space? Humility, because the answer is not decided by a feeling of mystery. It is decided by data. Maps of the cosmic microwave background, the distribution of galaxies, the curvature of space, and possible repeated patterns in the sky all have to be tested. The more beautiful an idea is, the more carefully it has to be measured. And perhaps the greatest beauty of this story lies here. Even though we do not see ourselves as an old image returning from the edge of the universe, we are still seeing our deep past in a broader sense. When we look at the cosmic microwave background, we see a time before stars, before planets, before abundant heavy elements, before biology, before there were eyes to look. When we look at young galaxies, we see early stages of star formation, element formation, and structure formation. When we look at old stars and stellar remnants, we see where heavy elements were formed and scattered. These things are not the personal past of any one human being, but they are the material past that made every human being possible. A carbon atom in your body once had to be made inside a star, or through cosmic processes connected to the life and death of stars. An oxygen atom in your breath has a history longer than any memory. The iron in your blood, the calcium in your bones, and the elements in soil, water, rock, and living things all belong to a cosmic story stretching across many generations of stars. So when we look very far away, we do not see an image of ourselves as if in a mirror, but we do see the ancient stages where the conditions for ourselves were gradually prepared. The sky does not return our face, it returns our origin. If you think about it, this is a deeper and more peaceful answer. We often think of the past as something that has been lost, but in the universe, the past does not disappear in a simple way. Part of it is still travelling as light. Part of it is stored in the structure of atoms. Part of it is written in the distribution of galaxies. Part of it lies in the cosmic microwave background, cold and weak, but still measurable. The past does not remain intact like a movie we can rewind whenever we want. It is scattered through signals, matter, the geometry of space, and the limits that science is still trying to understand. The farther we look, the closer we get to the dawn of the universe, but that dawn does not open forever. It has an early fog, it has a horizon of light, it has regions that, for now, we can only understand through indirect traces. This does not make the story less wondrous. On the contrary, it makes the universe more real. A universe with observational limits is a universe where science must be patient, where it must not invent what light has not allowed us to see. Those limits are what give knowledge its dignity. We do not say that we know everything, we say that light has told us this much, and from there, we keep asking. At this point, the original question becomes more dangerous in the most beautiful sense of science. If looking far away means looking into the past, and if the universe is wide enough to hold ancient light, then could light from Earth's past be somewhere out there? Yes, it has left. It is spreading outward. It is growing weaker. It is becoming a part of an ocean of signals from which it would be almost impossible to separate. And if it could return, could a civilization far enough away, patient enough, and sophisticated enough see Earth as it existed before we were born? In the principle of distant observation, that touches a real possibility of light. But for us to see that light again ourselves, the universe would have to give it a path back. And that path, if it exists, does not belong to simple imagination. It belongs to the deep shape of space. So when we look up at the sky after this part, we can carry a clearer understanding with us. Distant galaxies are not just far away. They are young in our view. The cosmic microwave background is not just a weak signal. It is the light boundary of the universe's childhood. And the question of seeing ourselves is no longer just a strange-sounding question meant to spark curiosity. It is a thread connecting the speed of light, the age of the universe, the expansion of space, the era when the universe became transparent, and the possible shape of the entire cosmos. One small question has opened a very large door. We do see the past, but which past can become an image before our eyes depends on whether the light can truly reach the place where we stand. Now let us turn directly to the question that makes this entire journey feel both strange and frighteningly beautiful. If we look far enough, can we see our own past? After everything we have gone through, the answer is no longer simply yes or no. It is more like a door with two locks. The first lock is very clear. If you look far away, you are definitely looking into the past. But the second lock is much harder. Is the past you are seeing your own past? The past of Earth itself, the past of the very place where you are standing. To answer that, we have to follow the light that leaves this planet. Every day, Earth does not only receive light from the sun, Earth also reflects part of that light back into space. Light bounces off white clouds, blue oceans, bright deserts, ice at the poles, forests, cities, mountains, and even the thin layer of atmosphere surrounding the planet. In addition to reflected light, Earth also emits infrared radiation because the planet has its own temperature. Since humans began using radio technology, some artificial signals have also spread out into space. All of these things create an extremely weak, extremely thin but very real trace. Earth is constantly sending information about itself into the universe. Imagine Earth as a very small blue lighthouse in an enormous darkness. That lighthouse does not shine a powerful beam like a searchlight. It only reflects and emits faint signals that spread out in many directions. Those signals do not remain still around the planet. They leave at the speed of light. After 1 second, they have already crossed a distance greater than the distance between Earth and the Moon as a small part of their journey. After a little more than 8 minutes, sunlight finally reaches Earth, but the light reflected from Earth keeps moving outward. After 1 year, a layer of light from Earth has spread to a distance of 1 light year. After 100 years, it is 100 light years away from us. After 1,000 years, it has travelled 1,000 light years, as long as it has not been absorbed or scattered along the way. So in principle, Earth's past is out there. It is not inside a box. It is not inside a film reel. It is not sitting in one fixed place. It spreads outward as an expanding sphere of light, growing thinner and weaker over time. A layer of light carrying traces of Earth from 100 years ago has now travelled about 100 light years away. A layer of light carrying traces of Earth from 1,000 years ago is much farther out. Even older layers of light left this planet before humans had cities, when ancient forests and seas existed in different forms, and even when life on Earth was completely different from life today. If there were an observer 100 light years from Earth, and if that observer had a telescope so powerful that it went far beyond current technology, they would not see Earth as it is today. They would receive light that left Earth about a century ago. If they could distinguish this small planet from the brilliant light of the sun, they would see an old Earth. Not because they travelled backward in time, not because history was magically replayed for them, simply because light needs 100 years to travel from Earth to their location. For them, the observable present of Earth is our past. If there were an observer 1,000 light years away, they would receive light that left Earth roughly 1 millennium ago. They would not see modern satellites, they would not see city lights the way we have them today, and they would not see strong technological signs from the modern era. They would receive a planet with oceans, clouds, continents, ice, forests, and life. But the detailed signs of civilization would be so small that they would be almost impossible to see without extraordinary observational technology. If there were an observer millions of light years away, the light they received from Earth would belong to a time before modern humans appeared. Earth, in their view, if they could see clearly enough, would be a world far older than we are. These examples sound like science fiction, but the principle of light is entirely physical. Any distant observer sees objects as they were when their light left. The unrealistic part lies in the ability to observe fine details. Earth is very small, the sun is very bright. The separation between those two objects in the sky of a distant observer would be extremely tiny. The light reflected from Earth is far weaker than the direct light from the sun. Capturing an image of a small planet next to a bright star across a great distance is a massive challenge, even for modern telescopes observing much closer exoplanets. So we have to clearly separate two things. Past light is truly spreading outward, but collecting a detailed image of Earth from very far away is far beyond what is practically possible today. However, our main question is even harder. It does not ask whether someone very far away could see Earth in the past. It asks whether we ourselves, from here, can look far enough to see our own past again. And this is where everything changes. For a distant observer to see Earth's past, light only has to travel from Earth to them. But for us to see our own past, light from Earth would have to leave, travel through space, and then somehow return to Earth, or at least return to our telescope. In simple terms, Earth's past has to become light that is coming toward us, not just light that is moving away from us. This is the key point. Earth's past is flying out into space, but flying outward does not mean it will come back. A ray of light leaving a mountaintop, the ocean surface, or the roof of a city does not naturally circle back like a bird remembering its nest. In space that is nearly flat and has no special obstacle, light follows a locally straight path through space-time. It keeps moving forward. It grows weaker because its energy is spread across an ever-expanding sphere. It may be absorbed by dust, bent slightly by gravitational fields, or stretched in wavelength by the expansion of the universe if it travels across truly cosmic distances. but it has no natural reason to turn around and return to where it started. Let us use a very concrete image. If you stand in a dark room and point a flashlight at a wall, the light can reflect back to your eyes because there is a wall there. If the room has no wall, if in front of you there is only endless open space, the light will keep going. You cannot see that beam again simply by looking farther in the same direction, unless some object reflects it or bends it back toward you. Earth is the same. Space is not a room surrounded by walls. The observable universe has an observational horizon, but that horizon is not a reflecting wall. It is only the limit of the signals that have had enough time to reach us during the lifetime of the universe. Some people might imagine that if the universe has an edge, light from Earth would fly to that edge and bounce back like a ball bouncing off a wall. But that is not the correct scientific model. The universe does not have a physical edge in the way a room has walls. When scientists talk about the observable universe, they're talking about the part of the universe whose light has had enough time to reach us since the era when the universe became transparent. Beyond the observational horizon, there may still be space, there may still be matter, and there may still be galaxies whose light has not reached us yet. That horizon is an information limit, not a surface that light strikes and reflects from. So is there any way for Earth's light to come back? In principle, a few physical ideas can be considered, but none of them is simple. The easiest one to picture is a mirror. If there were a giant mirror placed 50 light years from Earth, light from Earth would take 50 years to reach the mirror, and then, if it reflected in the right direction, it would take another 50 years to return. In that case, we could see Earth from 100 years ago. But the universe does not naturally place a giant perfect mirror like that for us. And a mirror large enough, precise enough, clean enough, and properly oriented at that distance is not something that belongs to the natural astronomical reality we know. The second way is gravity. According to general relativity, mass and energy curve space-time, and light follows curved paths through that geometry. So light from a distant galaxy can be bent by a galaxy cluster in between, creating the phenomenon known as gravitational lensing. Sometimes the same celestial object can appear as multiple images because its light travels along different paths around a large mass. This shows that light does not always move like a simple straight line in everyday intuition. But gravitational lensing does not turn the universe into a convenient mirror that lets us see old Earth again. For light from Earth to return to the exact place where we stand, an extremely special gravitational configuration would be needed, and there is no evidence that such a configuration is producing images of our own past. The third possibility is deeper, and it also opens the door to a larger question: the global shape of the universe. If space is infinite, or if it is simply too vast compared with the distance light can travel during the age of the universe, then light leaving Earth will not have enough time or enough of a path to return. But if the universe is finite in a special way, like a space that can be closed without having an edge, then geometrically light could travel along an extremely long path and return from another direction. This is not about a wall at the edge of the universe. This is about the structure of space itself. A gentle example is the surface of Earth. If you travel across Earth's surface in one direction for long enough, you can return to your starting point without ever meeting an edge. That surface is finite but has no boundary. However, this is only a two-dimensional image to help intuition. The three-dimensional space of the universe is not Earth's surface, and we must not turn the example into a claim. But it helps us understand an important idea. A place can be finite without needing a wall. If the universe has a closed shape in some way, light could circle through the structure of space itself. If that were true, and if the overall size of the universe was small enough compared with the distance light has been able to travel, the sky could contain repeated images of the same region of space. A galaxy might appear in two different places in the sky, not because there are two identical galaxies, but because the light from the same galaxy reaches us along two different paths. One image could be younger, and another image could be older. In an extremely special case, if light from the Milky Way or from our own region of space had travelled around long enough and returned, then in principle we could see a past version of our cosmic environment. But that is a hypothesis depending on the geometry and topology of the universe, not something that has been confirmed. Scientists have searched for signs of such repeated patterns. One especially important place to test this is the cosmic microwave background, the ancient light left over from when the universe was only about 380,000 years old. If the universe had a closed structure small enough, the map of the ancient sky might contain matching circles or corresponding patterns, like repeated fingerprints of the same region of space. So far, precise observations have not provided solid evidence for a closed universe small enough to create such easily recognizable copies. In other words, we have not seen reliable signs that the sky is replaying the past of the very region of space we live in. This is where science needs honesty. A fascinating story may make us want to say, yes, if you just look far enough, you will see yourself in the past. But that statement would not be accurate. A better answer is this: when you look far away, you're looking into the past. But to see your own past, your own light has to come back, and right now we do not have evidence that the universe allows that to happen in an observable way. In some special models of the universe, the idea is not completely forbidden, but in the data we have today, it is not something we can claim as fact. We can say it this way: an outside observer, if they were far enough away and had unimaginable technology, could see Earth in the past. But for us to see ourselves, that light would have to do something much harder. It would have to return. And that requirement, the requirement that light must return, is what separates a physically understandable idea from an observational dream that has no evidence yet. A distant observer only needs to stand where Earth's light arrives. We, on the other hand, would have to wait for a path of light that left us to circle back to the right place. That is something entirely different. This also helps us understand why the past is not a place we can easily point a telescope toward. The past is information carried away by light. If that information is coming toward you, you can receive it. If it is moving away from you and does not return, you cannot collect it from your own location. A telescope is not a machine that summons light. It is a machine that listens to light that is arriving. It cannot open a window into any day that has already passed. It can only collect the signals that the real universe has actually placed on a path toward us. Here is a very thought-provoking example. When we observe a supernova in a distant galaxy, that event may have happened millions or billions of years ago. To us, it appears only now because its light has just arrived. But in other places in the universe, the light from that event may have arrived earlier, or it may arrive later. An event does not have one shared time of being seen for the whole universe. It has a sphere of light spreading outward. Each observer learns about the event when that sphere reaches them. Earth's past is the same. It does not turn into an image sitting somewhere for everyone to watch at the same time. It is a travelling signal, and an observer meets that signal only if they lie along its path. This does not make the question less wondrous. On the contrary, it makes it more precise. When we understand that Earth's past is spreading outward into space, we realise that this planet is always leaving traces behind. Every sunrise reflected on the ocean, every layer of cloud, every season of melting ice, every night when cities glow sends out a piece of information. Most of that information is too weak for anyone far away to decode. Most of it will drift forever without ever being read. But it is still a physical truth. The present does not close completely the moment it passes. Part of it keeps flying away as light. And if one day humans observe an Earth-like planet around another star, we will also be seeing that planet in the past. If it is 40 light-years away from us, we see it as it was 40 years ago. If we search for atmospheric signs such as water vapour, oxygen, methane and carbon dioxide, we are not reading the planet's absolute present. We are reading traces that left it many years earlier. Astronomy about life beyond Earth, if it exists, will always be astronomy of late arrival. Even if a distant world has oceans, clouds or biology, we only know that after its light has crossed the distance between two star systems. In a very strange sense, the entire universe sees itself through the past. No star is seen exactly as it exists at the same moment everywhere. No galaxy can send an instant image of its present to every observer. Every place lives in its own present, but can only know other places through signals that arrive late. This is not a small inconvenience. It is a basic structure of reality according to modern physics. The speed of light is not just a number. It is the limit of cause, information, and observation. When we place human beings into that picture, the original question becomes more emotional. We want to see ourselves in the past because the past has a deep pull on us. We want to know whether what has been lost still exists somewhere. We want to know whether the light of an old day, an old face, an old Earth, is still travelling on some path. Physics answers that yes, light from the past may still be moving, but physics also says that existing along a path does not mean it can return to the one who emitted it. A memory made of light may be moving away forever. Even so, we should not see the universe as a cold place because of that. The opposite is closer to the truth. Precisely because light leaves, every moment becomes part of a wider universe. An afternoon on Earth does not only vanish inside the mind of the person who lived through it, it also reflects light into space. An incredibly tiny part of it becomes a physical signal. Even if almost no one can read it, it still joins the symphony of information spreading outward. The universe does not preserve everything for us to watch again, but it also does not erase every trace immediately. If we return to the question in very simple language, the answer is this: you cannot just look very far in any direction and be sure you will see yourself in the past. You will see the past of objects whose light is coming from that direction. You can see old stars, old galaxies, the young universe, and the ancient background light. But your own past is not simply sitting far away like a picture hanging on a wall. It left you as light and travelled outward. For you to see it again, the universe would have to bring that light back. And right now, we do not know of any natural mechanism that is doing that for images of Earth's past in an observable way. That answer may not satisfy the imagination immediately, but it has the beauty of truth. It says the sky is the past, but not a personal mirror. It says the telescope is a time machine, but not a machine that rewinds human life. It says light stores information, but that information becomes knowledge only when it reaches an observer. And it says that to understand the universe, we do not only need to dream big. We also need to ask correctly: where did the light come from? How long has it travelled? And is it truly moving toward us? From here, the question opens into a deeper layer. If Earth's light does not naturally return in flat and open space, could the true shape of the universe change the answer? Is space infinite? Can it be finite without having an edge? Could light travel along extremely long paths and then appear again from another direction in the sky? Could the sky contain repeated images that we have not recognized yet? This is no longer a question about a stronger telescope. This is a question about the deepest map of space. And before we move on, hold on to one very clear image. Earth's past is flying outward into space like extremely faint ripples across a dark lake. Those ripples carry traces of ages gone by, but they spread farther out, growing thinner and weaker. Someone far away could meet an old ripple and see Earth as it once was if they had unimaginable power to read it. But we, standing at the place where those ripples began, cannot see them again, unless the lake of the universe curves in a way that brings the ripples back. That is why the question, if we look far enough, can we see ourselves, is not really only asking about light. It is asking about the shape of the entire lake on which that light is spreading. If the light from Earth long ago wants to return to us, then the question is no longer just how fast light travels or how powerful a telescope can be. The question becomes deeper. What is the shape of the space that light is moving through? This is one of the places where human imagination can easily run very far, but it is also where science has to move very slowly. Because when we say the shape of the universe, we're not talking about the shapes of galaxies, we're not talking about the pattern of stars in the sky, and we are not talking about a fireball expanding into some empty space outside itself. We're asking about the geometry of space itself. If light travels straight for long enough, does it keep going farther away forever? Or is there a possibility that it could return from another direction? In everyday life, we're used to space that feels almost flat. You place a table in a room, measure its length, width, and height, and everything seems very clear. Two parallel lines do not meet. A triangle drawn on paper has three angles that add up to nearly 180 degrees. If you turn on a flashlight in an open room, the light travels in a straight line until it meets a wall, dust, a mirror, or some other object. That intuition is very useful on Earth, but the universe is not required to obey the intuition of a small room. On very large scales, the geometry of space is a question that has to be measured with light, with the cosmic microwave background, with the distribution of galaxies, and with very careful mathematical models. There are three ideas that are often mentioned when people talk about cosmic geometry. Space may be nearly flat, meaning that on large scales it behaves like the familiar Euclidean geometry we know. Space may have positive curvature, in a certain sense like the surface of a sphere, but in 3 dimensions of space, where very long straight paths can behave differently from our intuition. Space may also have negative curvature, often compared with a saddle shape in a 2-dimensional example, where parallel lines tend to move farther apart. But examples like a sphere or a saddle are only images that help us imagine the idea. The real universe is 3-dimensional space, not a 2-dimensional surface placed inside some room. When scientists say space is curved, they do not necessarily mean that the universe is curving into some outside place. They are talking about how distances, angles, the paths of light and large-scale structures behave from within space itself. The important point is that curved and closed are not exactly the same thing. Geometry asks how space is curved. Topology asks how space is connected to itself. A space can be locally flat in its geometry, but still have a global structure that is stranger than our intuition, as in some mathematical models like a 3-dimensional torus. A simple image is an old video game. If a character walks off the right edge of the screen and appears again on the left edge, the world in that game can feel flat to the character, but it is connected to itself. Of course, the universe is not a video game screen, but this example helps us understand that space does not need to have an edge in order to be finite in a special way. This is exactly why the question, can we see our own past, is really the question, what shape and global structure does the universe have? If the universe is an infinite open ocean, light leaving Earth will keep spreading outward, becoming weaker and thinner, with no reason to return. But if space has some kind of closed structure, light could travel along a very long path, loop through the structure of space, and then appear again from another direction. In that case, in theory, we could see the same region of the universe more than once, but at different moments in its history. A galaxy might not have only one image in the sky. It could have multiple images, arriving from different light paths, each path carrying a different delay. Imagine standing in a very unusual hallway. It has no clear end wall. You keep walking straight ahead, and after a long journey, you return close to where you started without ever turning. In everyday life, this sounds absurd if we're thinking about a straight hallway inside a building. But on the surface of Earth, the idea is more familiar. If you travel long enough in one direction across the surface of the planet, you can return near your starting point. Earth's surface is finite but has no edge. Still, we have to be very clear. This is only a 2-dimensional example to guide intuition, not evidence that our 3-dimensional universe works exactly that way. It only opens a conceptual possibility. Space may not need a wall at the edge in order to have paths that return. If light from Earth could loop around like that, the story would become almost unbelievable. Light leaves the planet in a distant era, carrying a faint image of clouds, oceans, continents, and life. It travels through the universe on a journey longer than all of human history. Then one day, from some direction in the sky, part of that signal returns. If we had a telescope sensitive enough, sharp enough, and capable enough to separate that extremely weak signal from every other source of light, we might see Earth as it once was. But that imagined sentence already contains far too many ifs. If space is closed in exactly the right way, if the universe is small enough for light to complete the loop within the age of the universe, if the signal has not been weakened beyond recognition, if it has not been completely lost in the background light, if we know exactly what sign to look for. Science is not allowed to ignore those ifs. Cosmologists have actually searched for related signs. One special place to look is the cosmic microwave background, the ancient light left over from when the universe was only about 380,000 years old. This radiation comes from a very distant sphere in our observable past, often called the surface of last scattering. If the universe had a closed topology small enough, light from the same region of the early universe could reach us from multiple directions. In that case, the map of the cosmic microwave background might contain repeating patterns, such as circles with matching temperature fluctuations. This search is often described with a very understandable image, looking for matched circles in the ancient sky. What is worth noticing is that modern observations are not just guessing. Satellites such as the Wilkinson Microwave Anisotropy Probe and Planck have mapped the cosmic microwave background with very high precision. From that map, scientists can test the curvature of space, study the distribution of temperature fluctuations, and search for unusual signs that might suggest a special global structure. The results so far are cautious. The observable universe appears to be very close to flat on large scales, and there is no solid evidence for a closed structure small enough to create clearly repeated images. In other words, if the universe has a complicated global shape, it does not reveal itself in a simple way within the part of the universe we can observe. This does not mean science has proven that the universe is definitely infinite. This is a very important point. When we say the observable universe is close to flat, that does not automatically mean the entire universe is infinite. A very small part of an enormous curved surface can also look nearly flat if you only examine a small region. On Earth, a field may look flat to a person standing on it, even though the entire planet is spherical. In the same way, if the whole universe curves very gently on scales far larger than the region we can observe, current data may only show that it is nearly flat within our field of view. So the accurate statement is this: within the observable universe, current measurements are highly consistent with a nearly flat geometry. The larger universe beyond that may still be outside our direct observational reach. This distinction is what keeps the story both scientifically correct and still wondrous. We cannot confidently say the universe is a giant hall of mirrors because there is no evidence for that. We also should not confidently say the universe is absolutely infinite because the region beyond the observable universe cannot be directly measured in a simple way. What science allows us to say is this: current observations do not show that Earth's light has looped around the universe and returned so that we can see ourselves. If a closed structure exists, it must be subtler, larger, or harder to detect than the clear signs in the cosmic microwave background have shown so far. Another way to understand this is to think about size. Light has only had a finite amount of time to travel since the universe became transparent. If the universe has a closed structure but its total size is much larger than the distance light can travel during the age of the universe, then we still would not see light looping back. It is like living on a planet so enormous that even if you walked straight ahead for your entire life, you would never realize you were on a curved surface. For us, the observable universe is the part of information that has had time to arrive. The region beyond it may be much larger. If the loop that light would have to travel is longer than the age of the universe allows, then even if space is mathematically closed, we still cannot see past copies of ourselves. At this point, the phrase far enough has to be understood differently. Far enough is not a magic spell that can break every limit. In astronomy, looking farther means receiving older light from sources that are sending light toward us. But if the source is Earth itself in the past, that light initially moved away from us. To see it again, distance is not the only factor. We need a path back. We need the geometry or topology of space to allow it. We need the light to have not been scattered so much that it has completely lost any recognizable identity. We need data showing that the sky truly contains repeated images, and right now, that chain of conditions has not been satisfied in observation. This also helps us avoid a common misunderstanding. The fact that the universe is expanding does not mean galaxies are flying out from a center into an outside emptiness, like shrapnel from an explosion. In modern cosmology, expansion is the change of distances within space itself on large scales. There is no special center from which everything is being launched. Every observer on cosmic scales can see distant galaxies moving away according to the expansion pattern. So when we ask whether the universe has an edge, we should not imagine a ball of matter expanding inside a dark room. The better question is, what overall curvature does space have? What topology does it have? And how does the part we can observe relate to the full structure? If the universe were a giant room of mirrors, light could create repeated images. But the universe does not show simple signs of being that kind of mirror room. If the universe is an infinite open ocean, light from our past simply drifts away forever. But we also cannot step outside the whole universe, look at it from the outside, and confirm everything through intuition. So the best answer is not an overly dramatic one. The best answer is the answer of a scientist. In theory, some models of space could allow light to loop around and create repeated images, but current observations have not found evidence that this is happening in our universe on a visible scale. That caution is what makes the story trustworthy. In science, an idea is not rejected simply because it is strange. But it is also not accepted simply because it is beautiful. It has to leave a measurable trace. If the universe has a closed topology small enough, the sky could contain repeating patterns. If there are repeating patterns, the cosmic microwave background or the distribution of galaxies could contain signs. If those signs are clear enough, scientists can test them with data. So far, strong searches have not produced a confirmed detection. Therefore, scientific honesty requires us to say, it can be imagined, it can be modelled, but there is no observational evidence yet that we are seeing our own past. Even so, notice the beauty of the question itself. It forces us to move from a very human feeling all the way to the edge of modern cosmology. We begin with a close and familiar wish. Is the past still somewhere we can look back at? Then we learn that light preserves information. We learn that every view into deep space is a view into the past. We learn that Earth's past has left the planet as faint light. And finally, we realize that to see that past again, we have to ask about the shape of all space. A question that first sounds poetic has led us to differential geometry, the cosmic microwave background, cosmic topology, and the limits of observation. There is a great humility in this. We are small creatures on a small planet, but with light and mathematics we can ask whether space is flat, whether it is curved, whether it is closed, and whether it repeats itself. We do not stand outside the universe and look at it like an object on a table. We are inside it, using the signals that reach us to infer the structure of the place where we live. This is like a person born inside a dark room, unable to leave, but able to listen to echoes, measure the direction of sounds, measure response times, and gradually understand the shape of the room. The difference is that our room is the universe, and its echo is ancient light. So if one day there is evidence that the universe has a closed structure, what would change? First, it would not turn science into myth. It would open a very serious new chapter. Astronomers would have to determine the fundamental size of space, which directions are connected to which other directions, the possible appearance of repeated images of galaxies, and how light travels through the entire structure. If one galaxy appeared multiple times in the sky, we would have to prove that it was truly the same galaxy at different moments, not just randomly similar galaxies. Scientists would need to compare spectra, stellar ages, shapes, surrounding environments, redshifts, and a great deal of other data. Such a discovery would be enormous, but it would also have to meet a very high standard of verification. And if the universe is truly infinite, or at least so vast that no ray of light from Earth can loop back during the age of the universe, then our own past will not return as an image. It will continue to spread outward. It may pass through distant star fields, blend into the background of signals, and weaken until it becomes impossible to distinguish. But that does not mean the past turns into nothingness immediately. It only means the past is not stored for us personally, the way a mirror stores a reflection. The universe does not promise to return every ray of light. It simply obeys its own geometry. And perhaps this is the most mature answer we can receive. We do not need the universe to become a hall of mirrors in order to feel that we belong to it. Even if Earth's light does not return, the sky still shows us a much larger past. When we look at the cosmic microwave background, we see the childhood of the universe. When we look at distant galaxies, we see the era when structure was forming. When we look at old stars and stellar remnants, we see where matter was transformed to create heavy elements. When we look at Earth itself, we are standing on the result of that history. Our own past does not necessarily have to appear as an old image out there, because it has already been written into the matter that makes us. The question, what shape does the universe have, is therefore not only a question of mathematics, it is a question about the possible fates of light. In an open space, light travels outward forever. In a closed space small enough, light can return. In a nearly flat but enormous space, light may travel for so long that it never completes a loop during the time the universe has existed. Each possibility gives us a different kind of sky, a different kind of past, and a different kind of limit. And in every case, one core point still stands. Looking far away means looking into the past, but almost certainly not our own past in the direct sense we usually imagine. If one night you look up at the sky, remember that what you are seeing is not the entire universe. It is the part of the universe that has had enough time to send light to you. What lies beyond that range does not necessarily fail to exist. It simply has not yet been able to speak to us through light. and if there are closed paths in the deep shape of space, they have not yet left clear evidence that our own light has returned. In that silence, science does not rush to fill the gap with certainty. It lets the gap remain a gap and then keeps measuring, keeps asking, and keeps looking. So the question, can we see ourselves, does not end with a door slamming shut. It ends with an open hallway. At the beginning of the hallway is light leaving Earth. In the middle of the hallway is the geometry of space. At the far end of the hallway is data that we do not yet have or may never have enough of. But along the way, we have learned something profound. The universe is not only a place that contains objects, it is the place that decides where memories made of light can go, whether they can return, and whether they can become knowledge for any observer. If the universe is an open ocean, the light of our past will drift away forever. If the universe is a very subtle closed structure, light may have stranger paths. But for now, based on what has been measured, we live in a universe that appears nearly flat, vast, and without solid evidence of that time mirror. And precisely because it is not certain, the story remains alive. Every better map of the cosmic microwave background, every deeper galaxy survey, every more precise measurement of curvature, and every new generation of telescopes can tighten the answer. They may continue to tell us that space is too vast, too close to flat, and that our light does not return. Or they may find some subtle sign that changes the way we understand the entire sky. But until then, the most honest answer remains this. We are looking into the past of the universe. Our own past is flying outward into space, and there is not yet any evidence that it has looped back to become an image in our eyes. If the cautious scientific answer is that we are almost certainly not seeing an old image of ourselves out there, that does not take away the beauty of the original question. On the contrary, it opens up a deeper kind of beauty. Because even though the sky does not give us back a time mirror, it still gives us a cosmic family tree. We may not see our own face from yesterday in some distant point of light, but when we look deeply into space, we are seeing the ancient conditions that made that face possible in the first place. We are seeing the past of light, the past of matter, the past of atoms, and the past of the very stage on which life eventually appeared. Notice this very subtle difference. A mirror gives us an image of the surface. It gives back a posture, a face, eyes, hair, the things appearing in one brief moment. But the sky is not that kind of mirror. The sky does not say, "This is you from 10 years ago. This is your old house. This is an afternoon that has been lost." The sky speaks in a much older language. It says, "This is light from the time when galaxies were young. This is the afterglow from when the universe first became transparent. This is matter that once lived inside stars. This is the long road by which hydrogen, helium, carbon, oxygen, iron, and many other elements travelled from the furnaces of the universe into rock, seawater, air, and finally living bodies." So when we ask, can we see our own past? Perhaps we're asking the question too narrowly. If ourselves only means a personal image, a private moment, a figure standing on Earth in the past, then science has not given us evidence that that light has returned. But if ourselves means the entire chain of causes that made our existence possible, then every deep look into the universe is a look into our own past. Not the past as a diary of one human life, but as a material record stretching across billions of years. We do not see ourselves in a mirror. We see the origin of the possibility of having a self. Starlight is the memory of matter. It has no consciousness, no purpose, and no awareness of the information it carries. But in its wavelengths, in its colours, and in its spectral lines, there is history. A hot blue star tells us about extremely high temperatures and usually a shorter lifetime. A cooler red star tells us about another state of stellar matter. A stellar remnant tells us about the end of a star's life, where gravity, temperature, and pressure once operated at levels far beyond everyday experience. When that light reaches a telescope, it does not only create an image, it carries the fingerprints of atoms, heat, motion, and time. The cosmic microwave background goes even deeper than that. It is like a cold whisper from when the universe was very young. Not a whisper made of sound, because sound does not travel through a vacuum the way it travels through air. It is a nearly uniform background of radiation, left over from when the universe was only about 380,000 years old, when light first became able to travel freely through space. Before that moment, the universe was like a thick, hot fog to light. After that moment, ancient photons began their journey. More than 13 billion years later, they are still reaching us, stretched into microwaves by the expansion of space. This is not a picture of a star or a galaxy. It is the thermal memory of the entire observable universe. Distant galaxies are also memories, but they are memories of the formation of large-scale structure. When we look at an extremely distant galaxy, we are not seeing a mature city of stars in its present state. We are seeing the stage when its light left it, when the universe was younger. Those faint points of light can tell us how quickly matter gathered together, how intensely stars began to form, and how small galaxies merged into larger ones. Every distant galaxy is an old page in a book the universe does not write with ink, but with hydrogen, helium, dark matter, gravity, and light. And then, when we lower our gaze from distant galaxies back to our own bodies, the story does not become smaller. It only changes scale. There is iron in the blood, there is calcium in the bones, there is carbon, oxygen, nitrogen, phosphorus, and many other elements in the cells. Those elements did not simply appear on Earth out of nothing. Most hydrogen comes from the very early universe. Many heavier elements were created in generations of stars, in stellar cores, in stellar explosions, and in other violent cosmic events. A living body, from the point of view of physics, is cosmic matter that has passed through a very long history before it could organize itself into breath, heartbeat, nerves, memory, and consciousness. This is not a poetic line meant only to comfort us. It is the science of the origin of elements. Stars transform lighter elements into heavier ones through nuclear reactions. Some massive stars, when they reach the end of their lives, throw material back into space. Those enriched clouds of matter can later take part in the formation of new generations of stars, new planets, and planetary systems like our solar system. Earth formed from a disk of material around the young sun. Inside that disk were grains of dust, minerals, ice, metals, compounds, all gradually coming together through gravity and collisions. From that process, a rocky planet was born. On that planet, over a very long time, chemistry became more complex, life appeared, evolved, and eventually produced beings capable of looking up at the sky and asking where they came from. So when we say that we live among layers of the past, that is true in many ways at once. Sunlight is the past by about 8 minutes. Moonlight is the past by a little more than 1 second. Starlight is the past by many years, many centuries, and many millennia. Light from distant galaxies is the past by millions or billions of years. The cosmic microwave background is the past from very close to the first transparent dawn of the universe. And the matter in our bodies is the chemical past of stars, interstellar clouds, the young solar system, and early Earth. We do not only look at the past, we are made from the past. Perhaps that is why the night sky always creates a feeling that is hard to name. It is both strange and familiar. Strange, because galaxies exist beyond every ordinary human distance. Familiar, because the matter in them and the matter in us belong to the same universe, following the same laws, the same periodic table, the same gravity, and the same light. When we look up at a band of stars, we are not only looking outward, we are looking into a larger version of the story already present within ourselves. We are a very small part of the universe, but we are not separate from the universe. We are not standing outside it, observing something else. We are matter from the universe, learning how to observe the universe. This makes the original question gentler. If we cannot see an old image of ourselves from a ray of light returning to us, we still do not lose our connection with the past. We simply understand that this connection is not found in a personal photograph. It lies in a much larger chain of cause and effect. Before there could be an eye to see, the universe had to have light. Before there could be a brain to ask questions, the universe had to have atoms, molecules, stars, planets, stable environments, complex chemistry, and time. Before there could be a person standing under the sky had to spend billions of years creating the conditions for that person to exist. We often think of the past as something behind us, but in astronomy, the past is everywhere. It is above us when we look at stars. It is far away when we look at galaxies. It is in the ancient microwave background when we measure the sky with sensitive instruments. It is in old rocks on Earth, in fossils, in the oceans, and in the atmosphere. It is in every atom that passed through earlier stages of physics before becoming part of a body. The past is not only time that has gone by. The past is the structure that is still holding up the present, and the present is not standing still either. Right now, Earth is still sending out its light and radiation. Faint signals from this planet are still leaving us, travelling through space, expanding like thin ripples across the surface of a dark lake. Light reflected from today's clouds will become the observational past of some place in the future. Weak radio signals from technological civilization have also been moving outward through space for more than a century, even though they become weaker and harder to recognise as distance increases. Every moment on Earth does not only pass through the memory of the people who live it. A very tiny part of it is also sent outward through physics. Maybe no one will ever read those signals. Maybe they will thin out until they become impossible to distinguish from the noise of the universe. Maybe they will never meet an observer close enough, sensitive enough, or patient enough, but that does not make them less real. The universe does not need an audience for light to travel. A photon does not have to be received in order to have existed. Earth's past is flying away, even though it almost certainly will not return like a movie for us to watch. And that thought is both a little sad and beautiful, because it says that every moment is small, but not completely sealed shut. When we understand this, the idea of seeing ourselves also changes. There is one kind of seeing with the eyes, which needs images, outlines, and surfaces. But there is another kind of seeing through understanding. When we know that the carbon in our bodies has a stellar history, we see ourselves in a deeper way. When we know that the oldest observable light comes from when the universe was still very young, we see the setting where all later structures began. When we know that distant galaxies show the era when the universe was still building its first cities of stars, we see the opening chapter of a story that Earth would later belong to. That is not an image of you in the past, but it is the history that made it possible for you to stand in the present. An astronomer does not look up only to count stars. They look up to understand how time turned matter into structure. A physicist does not measure light only to get a number. They measure light to know which atoms emitted it, what temperature created it, what motion stretched it, and what gravity bent it. An ordinary person looking up at the sky can also feel this in their own way. We do not need to know every equation to understand one basic truth. The sky is where the past arrives late, and in that late arrival, the universe allows the present to meet ages that our bodies could never travel to. This also helps us slow down in the story of the video. A video about the universe does not need to chase one shocking moment after another. The truth itself is already overwhelming if we give it time. Light from a distant galaxy may have travelled longer than Earth has existed. A photon from the cosmic microwave background may have begun its journey before there were stars, before there were planets, before there was complex chemistry as we know it. An atom in the body may once have existed in a stellar environment, or in a cloud of matter between stars before it became part of a planet. These things do not need exaggeration. They only need to be said correctly, slowly, and calmly enough for the mind to feel them. And from here, the question of our own past no longer feels like a simple puzzle. It becomes a way to understand humanity's place in the universe. We are not the centre of space. We are not a special point to which all light must return. The universe has not built a giant mirror just so we can see ourselves again. But we are not strangers either. We are the result of a history so long that it is hard to imagine. We were born in a universe capable of making stars, making elements, making planets, making chemistry, and in at least one place that we know of, making life that can ask about its own origin. Perhaps the maturity of knowledge lies in accepting both things at once. On one hand, we are not the main character of the universe in a naive sense. Light does not return simply because we want to see ourselves again. Space is not necessarily designed like a mirror room for human beings. On the other hand, we are still a real part of the universe. Our bodies, our breath, our memories, and the questions we ask all belong to the material evolution of the universe. We are small but not meaningless. We are brief but made from a very long history. Seen in this way, every star is an echo. Not an echo of sound, but an echo of a physical event. A star emits light. That light crosses empty space, and many years later it touches an eye or a telescope. Every distant galaxy is an old page, not because it's frozen in the past, but because the version we see is the version whose light left long ago. Every dark region is a pause where light has not had time to arrive, or is too weak for us to detect, or is limited by the observational horizon. The sky is not silent because it has nothing to say. It is silent because it speaks through signals that are slow, thin, and ancient, and that slowness can soften the human heart. In everyday life, the present is often too loud. Everything demands fast reactions, fast answers, fast conclusions. But the universe is different. The universe sends light across millions and billions of years. It is not in a hurry. It does not explain itself in a short sentence. It lets photons travel through space, lets atoms form through many generations of stars, lets galaxies grow through collisions and mergers, and lets life emerge after a long chain of conditions. When we listen to the universe, we also learn another kind of patience, the patience of light. If there is one feeling to hold on to at the end of this main section, it is not disappointment that we cannot see our old selves out there. It is a quiet gratitude that we can understand part of the story at all. A small creature on a small planet has built telescopes, detectors, satellites, equations, models, and maps of the sky in order to read ancient signs. We cannot step outside the universe and view it from the outside, but from within it, using light that arrives late, we can still infer its age, history, structure, and the material origin of ourselves. That is a very strange thing, and a very beautiful one. So perhaps the more beautiful answer to the original question is this. If you look far enough, you are looking into the past, but you are almost certainly not seeing yourself as an old image returning to you. Instead, you are seeing a past much larger than the self. You are seeing the layers of time that built the stage of existence. You're seeing light from when the universe was young, galaxies while they were still forming, traces of matter from before Earth existed, and stellar furnaces that once created many of the elements needed for life. The sky does not give us back a personal photograph. It gives us back a cosmic family tree. And now, the original question is no longer just a thought experiment. It has become a doorway. Behind that doorway are light, time, the shape of space, the limits of observation, the origin of elements, and a very quiet truth. Everything we see has left the place where it was born before it reaches us. Light leaves a star before it reaches the eye. A signal leaves a galaxy before it enters a telescope. Ancient radiation leaves the early universe before it becomes data in a map of the sky. Even our own present is leaving here, one photon at a time, to become the past of some faraway place. Somewhere in the universe, the light of old Earth may still be travelling through the darkness. Maybe it carries an extremely faint trace of blue seas, white clouds, forests, ice and snow, deserts, seasons that have passed, and civilizations that have changed. Maybe no one will ever see it. Maybe it will never return. But it did leave, and that is enough to remind us that we live not only in space, but in an expanding web of time. Every place sees every other place through a delay. Every act of seeing is a late meeting. Every light is a greeting from before. If the sky is a symphony, it does not play every note at once. It lets old notes arrive later, deep echoes come late, and long silences stretch between the stars. A telescope is only a large ear for light. A curious mind is only the place where those signals become a story. And in that story, we realize that the past is not only behind us, it is overhead, far away, in wavelengths, in atoms, in the structure of the sky, and in the very existence of the person listening. So when night falls and the sky grows darker, we can look up with a new feeling. Not to search for a mirror made just for us, but to recognize that we belong to a larger stream of history. Every star is a small door opening into a moment that has already passed. Every distant galaxy is a piece of memory from a universe still growing up. Every dark region is a reminder that there are still many things light has not brought to us yet. And every breath we take, however small, is still made from matter that has travelled through a journey longer than any human life. We may not see ourselves in the past out there, but when we look deeply enough, we see the ancient road that led to us being here, in this moment, under this sky, asking that question. If we look far enough, are we looking into our own past? After this journey, the scientific answer is clearer, but also more deeply reflective. We are certainly looking into the past every time we look far out into the universe, because light always needs time to travel from the place where it was born to our eyes. Moonlight reaches us after a little more than 1 second. Sunlight reaches us after about 8 minutes. The light from distant stars and galaxies reaches us after many years, many millions of years, and even many billions of years. So the night sky is not a direct image of the present. It is a stream of memories made of light. But according to what science currently knows, seeing our own past as if in a cosmic mirror still has no observational evidence. For that to happen, light that once left Earth would have to travel through space, and then, through some special geometric structure, return to us. In a vast universe that appears nearly flat and has not shown clear signs of repeated images like that, Earth's past may be flying outward, but that does not mean it will come back. And perhaps that is the quietest beauty of this story. The universe does not give us a mirror so we can look back at our own face from long ago, but it gives us something greater, a family tree of light and matter. We have learned that the telescope is a tool for looking backward in time, that the cosmic microwave background is a trace from when the universe was still very young, that distant galaxies are old pages from the formation of structure, and that our own bodies are made from elements with a deep stellar history. So when you look up at the sky, you're not only looking out into space, you're looking back toward the layers of time that quietly prepared the way for your own existence. Every starlight is an echo, every dark gap is a question that has not yet arrived, and every ray of light that touches our eyes has already left its home before becoming part of the present. Now, let those great thoughts settle gently. Let your body rest, like a small planet turning quietly in the dark. Thank you for staying with Drift into Quiet Knowing on tonight's journey. I wish you a good night of deep, peaceful sleep, and I will see you again on the next journey, where we continue listening to the gentle secrets of the universe.